Hello and welcome into a short demo of CENOS busbar heating application. Today we are going to build a simple three-phase busbar simulation using CENOS. We start by prepping our geometry. We can either build the geometry using the Advanced Geometry Editor, but I always say you don't need to use or learn another CAD if you already have a CAD design tool yourselves. So if you do, you can simply export your CAD file from the designated tool. It could be any Autodesk, SolidWorks products or anything. You export the geometry in a step file format and import it directly into CENOS to use it as a base for the simulation. So that's what I'm going to do. I will click the From CAD approach and select my CAD file. Once the geometry is loaded, we need to create the ambient air domain around the system where the magnetic field will be calculated as it propagates around the bus bars. So for this, I'm going to click Yes and select busbar terminals as the reference planes for the air domain, like this. Now CENOS has generated the air domain and we can actually move forward right now with the physics. Now before we do that, let me tell a bit about this stage. So right now we are at the geometry roles section, which is sort of an intermediate step between the geometry import and physical definition. Here we don't specify any physical parameters such as frequencies, applied currents, powers or material properties, but here we explain the purpose of each of the geometry part in our system. So right now, as we just selected the terminals as the reference points for air domain, all the busbar domains have been applied automatically. If we have any additional parts in our system, some conductive elements, additional busbars or whatnot, then you can easily add another geometry role. If we want to simulate the heating for one of the busbars, for example, we need to also specify the busbar surface right here. So to do that, we can add a busbar surface group. We can filter the faces, for example, for the first busbar, select all of them, deselect the terminals, and assign busbar surface. And that's it. So in this example, we are going to actually enable also the heating of one of the busbars to show how it is done. Once the geometry roles are set, we can go further into the physics. Now, physics is divided into different tabs. Here we always start with the simulation control, where we have the general system parameters and the, general definitions. So we can choose between AC and DC analysis, and we can choose between steady state or transient analysis. So for example, if we go with the transient AC analysis, we need to define the alternating current frequency, which could be, for example, 100 Hz, it could be higher, it could be lower, it really depends on the application. Then we define the end time, which could be anywhere between a second or less or up to a couple of hours, so also no limitations there. So for this I will put, for example, 10 seconds. And then we also need to specify the calculation time step, which for now I will put as 1 second, but you can use also the adaptive time step, which will then select the time step size automatically. Busbar definition itself happens very simply. We go into the first busbar tab. So for this, you do remember that we had enabled the external surface geometry role as well. So for this, the electromagnetic analysis has already been set. The material as copper has already been set. And we can see that we can already specify the applied current. So let's say 20 kiloamps. And we can also define the phase. So in this case, we want to define a phase shift between the three busbars. So I will define for this one a phase shift of 0, but then for the rest, I will set a different phase shift. If we want to also include thermal analysis of the busbar, we can very easily enable it like this. And here we then need to define the thermal losses on the surface of the busbar. So here we can enable either convective or radiative losses. So I can just go with the room temperature convection. And since the busbars will not be heating up that much, I will not include radiation at all. And that is it. So now we just need to repeat the same thing for the other busbars. So for this we set 0 degree phase shift, so for the middle one, then I will enable 120-degree phase shift with the same applied current. And then for the last bus bar, we are going to enable phase shift of 240 degrees, also with 20 kiloamps. Now, if you have anything else in your system, any conductive domains or whatnot, then for those you will need to define the material directly. And for that you can use our material library, which consists of quite a lot of different steels and different material properties, which you can simply select and pick. If you don't find your material here, you can very easily create a new material, which will then give you a blank template, which you can predefine with your own material properties, save it in our material library, and then afterwards use it without the need of defining it every time you want to use it in a simulation. Now, once the physics is done, you can either click Run or you can take a look at the mesh. So the meshing is done automatically, but we can also generate the mesh before the calculation starts to make sure that the mesh actually looks good and to sort of estimate the mesh size. Meshing algorithms are quite good. So as I said, they can be used by default. So here we see the generated mesh. We can see a very nice refinement at the places where the geometry has smaller details, for example, these internal fillets or so. And from the top, we can also see the automatically generated skin layers, which are there to account for the skin effect. Now, if we do want to change something, that's very easy to do. We can enable mesh refinements, select any of the busbar domains, and change either the skin layer setup, the total size of the mesh, or just pick and define mesh refinements locally. Once the meshing is done, calculation can be run, and the simulation results will appear once the calculation is finished. So the results will be displayed in a different window in ParaView. So by default, you are going to see thermal distribution of the busbars. So here we have the same system simulated for the same 10 seconds, but with the temperature enabled for all 3 busbars. So first of all, we can evaluate the dynamics of the heating. So we can go to the very beginning, click play, and see how the temperature evolves. We can see where are the hotspots, which give us kind of an idea of any kind of changes that we might want to do for the geometry, or maybe apply some external cooling or something like that if we see that our busbars are actually overheating. On top of the temperature, we can also analyze different fields for the results. So we can select the busbar of interest and switch between temperature to Joule heat, to current density, to magnetic flux density visualizations, all within the same view. On top of the visual results, we can also see numerical parameters of the system. The overview can be seen right here into the time charts, where we can see the active power, this distribution between the busbars, which gives us a very good sense of the efficiency of the system and the actual losses and where they go. We can see the current voltage and inductance values, but if you want more information, then together with the results, a CSV file is also generated, which consists of the same values that you just saw in the time charts, but here you can find additional parameters. For example, for the busbars, you can visualize not only the current voltage and other parameters, but for example, inductance, resistance, reactance, and impedance, which helps with more in-depth result analysis as well. Thank you for listening, and good luck in your next simulation.